So welcome to the inaugural Grasp Game Theory Seminar. So I'm going to be talking about Shapley Values and their applications to Explainable AI. So some background, in case you haven't taken a combinatorics class ever or recently. Permutation is where order does matter. So ABC and CBA are not the same thing, right? They're considered distinct. For combinations, order does not matter. So CBA and ABC are the same thing, but AC and AB are distinct, right? So that's the difference. And then the power set is the set of all subsets of a given set, i.e. every combination. So these are like perhaps relevant things to remember. I mean, I could never remember the difference between permutation and combination. So like, hopefully this helps some other people as well. So let's first talk about Shapley values, and that's the underlying principle for all today's talk. So they were developed by this man. His name's Lloyd Shapley, and he developed them in the 1950s for what's called cooperative games, right? So under cooperative game theory. And the idea is that you have multiple agents who are not competing against one another, but participating together. And so this was able to be used for things like modeling the economy, and it actually helped him win the 2012 Nobel Prize in Economics alongside Alvin Roth. So the motivating example behind all of this is imagine a group of farmers who are working together to grow wheat. Collaboration between the farmers causes differing outputs of wheat. So they're not simply the sum of the amount of wheat that they would generate if they each worked individually, right? They could collaborate, they could share they could share tools, they could share knowledge, etc., or they could fight with each other and actually produce less wheat than if they all worked individually. So the question is, how do you assign credit to each farmer for the total production of wheat, right? So that's essentially the underlying motivating example. You have this black box where these farmers are cooperating in some form or another. How do you assign this sort of credit? So what do you want out of this credit system, first of all? Well, a couple obviously useful properties are one, efficiency. The idea is that if you take the credit assigned to each farmer and sum them all up, the sum of all of the credit should equal the total wheat produced. It doesn't make sense that you assign some credit to each one, and when you sum it all up, it would be a different value. That seems not to be a very useful credit assign. Another one is a farmer who contributes nothing gets no credit, right? Because if someone's a freeloader and literally didn't do anything, then they should not be assigned any credit under a sensible credit system. Additionally, you have this notion of symmetry. That is to say, equal contributions get equal credit. So if two farmers are identical, then one farmer should not get all the credit and the other should get none. It should be shared equally across them. So symmetry. And then finally, you have linearity. The notion that if farmers were involved in back-to-back harvests, the exact same set of farmers, the credit they got from harvest A and harvest B should be able to be summed together if you just group the harvest into one big harvest. It's this idea where they play two sub games. You could just imagine it being a big game. Well, in the same way, you have like harvest for the first half of the year and harvest for the second half of the year. If you combine that into one big harvest, the credit that each farmer gets for each half should just be the credit that they get for the whole thing. And so these are the underlying properties that we want for our credit system. And it turns out that Shapley values are these credit values. And what I mean by that is any credit systems that uphold these properties must mathematically be Shapley values. That is to say that these are the necessary and sufficient conditions to characterize Shapley values.
Okay, I have a question, Kyle. So
yeah.
The first three axioms make sense, and they're kind of reminiscent of, like, I don't know if anyone's familiar with like Arrow's theorem and voting theory, but they're the things you would want. But the last one, linearity, I'm not sure why the relationship has to be linear. Is there some motivation for that?
It seems intuitively reasonable that if a farmer contributed very little in game one and very little in game two, their overall contribution to be the sum of their individual contributions, right? Like if it weren't linear, then it would be something else. It would either be they participated a lot in game one and game two, but the sum was somehow less than that total. Or they didn't do very much in game one and game two, but their sum somehow is more. right? If you violate linearity, you end up with these non-intuitive outcomes.
Well,
And
by
so you
linearity, you mean additivity.
the literature refers to this as linearity, right? The
Okay.
literature refers to it as efficiency, dummy, symmetry, and linearity.
Well, you're basically saying that the payoff for, in set theoretic terms, the payoff for A union B is the payoff of A plus the payoff of B. Is that correct?
Correct. And the caveat here is you're playing the game with the same set of agents. So you didn't have some farmers drop in and drop out.
Okay, sure.
Right?
All right.
So exactly the same people played in both cases. So exactly the same set of farmers were participating in both harvests.
Cool.
So these Shapley values are credit values. So let's talk about the farmer example from the perspective of permutations. So assume that we have P farmers and they're in the set F. And we have some model of productivity where we have a ordered set of farmers. It might not be all P farmers. It could be a subset of the farmers. And note that they are ordered. And the output is a real value corresponding to wheat output. So you might imagine that if you were forming a coalition of farmers to participate, the order in which you assign farmers might impact their output, right? So like the first farmer might say, immediately let's work with the second farmer, and the second farmer might immediately say, let's work with the third. If you were to order it differently, the first one would then, in the original example, work with the third one, and then the third with the second, and the relationship isn't necessarily totally transitive. I'll give an example shortly where such an example becomes clear. But note that this is an actually ordered set. And so ordering can impact the output. And so that's something that we need to take into consideration when reasoning about this model V. So we have this model that determines their performance, and we need to then leverage it to provide a credit assignment for each farmer individually. So the general gist is, for each farmer I in the full thing, you take every permutation of farmers. Remember, that's a subset that's ordered that aren't I, and basically sum the difference between their contribution without I and then their contribution with I, right? And so this is essentially the marginal value of I. It's the over every single possible combination, ordered every single way, without I, and then including I, and if you sum that all up, you'll get the marginal value of I. So that's essentially the gist. And that stated in equation form is, as I said, every single combination of subsets of farmers, right? So this is drawing from the power set. Without I, over every single ordering, you include I and you don't include I, and you take the difference between the two. You just sum that all up. And then remember, F is the set of all farmers. So you take the factorial of its size just to normalize. And over all that sum is the credit assignment. And like I said, this is actually how you compute a Shapley value. So does that in a nutshell make sense to everyone? This is essentially the first pass of two passes I'm going to make at explaining Shapley values. You worry about the subsets and then you worry about the ordering. And the idea is you do every single subset with every single order. And when you just like include all of this together, you end up with the marginal contribution of farmer I.
Okay, so the only thing confusing here perhaps is that you worry about the order. So the payout for this one set ordered in one way and a permutation of that same set could be different, right?
Correct.
So all we're doing is dividing by all the permutations. So if we said, okay, we don't care about order, then we would basically, the inside sum, we would get rid of that and we get rid of this.
So I will present an alternative formulation shortly that allows you to abstract that away.
Okay.
We're going to provide a different definition, F instead of V, that abstracts away the ordering.
Okay.
And so when order does not matter, that suddenly doesn't have to do any combinatorics. It's simply a straight evaluation. So I'll show that shortly.
Thanks.
So I have another question.
Yeah.
So this V function is defined over, so the the two
Yeah.
the two sets here are different sizes, right?
Yes.
So
These are identical sets, and then you just append I to the end of it. But
okay.
yes, you're correct that these inputs are fundamentally of different sizes.
Wait, so V is sort of the outcome of the game, right? The outcome
Correct. It's the outcome of the game if you included the first S participants in this order, and then included I, minus the outcome of the game if you just included those participants in that order.
Okay, so you have so the game is not just defined for this n players, but it's also defined for n minus 1 players?
Correct.
Okay.
And you'll see that that suddenly means that it isn't practical on some other scenarios, and we'll get to generalizing that later, right? So a lot of generalizing this to like actually useful domains requires evaluating some of these assumptions.
Got it.
So one of the things I think that's worth pointing out is this, as written, is sharp P hard. Now, for those of you that don't know complexity theory, sharp P means that it's at least as hard as NP, right? NP is the class of problems that need to be solved with a non-deterministic Turing machine in polynomial time. And the idea is it's as hard as the counting problems associated with NP hard problems. So a classic NP hard problem is SAT, right? Finding a answering the decision problem, does there exist a satisfying assignment for a CNF formulated expression? The sharp P hard equivalent of that is counting all of the satisfying assignments. So when, of course, there does not exist one, the count is 0, but when there does exist one, the count is 1 or more. So this is the accounting problem associated with the NP hard problem of SAT, right? So that is an example. It turns out you can actually embed that sharp SAT problem inside Bayes nets. So doing exact Bayes net inferences is actually sharp P hard, which is why in practice you do Monte Carlo sampling from a Bayes net to approximate the conditional probability. And then computing the matrix permanent is another example of a problem that's sharp P hard. It turns out that that's actually the original sharp P hard problem. That was what defined the class of sharp P hard. So that's mostly trivia. Just know that it's hard. It's above P, and so assuming P does not equal NP. So that's something to keep in mind in terms of a limitation. So I told you that I'd give you an example of ordering where this might matter. It's called the glove game. So imagine player 1 is a right-handed glove, player 2 is a left-handed glove, and player 3 is a left-handed glove. And your goal is to form the maximum number of pairs of gloves. So obviously, the number of ways that you can do that is if you have player 1 and 3 together, you form a pair. If you have player 2 and 3 together, you have a pair. And if you have 1, 2, and 3, you have a pair. Otherwise, you just don't have a pair, right? So that's the full payoff matrix written in a shortened format that's like fits on a slide. And so this is an example of how you do the marginal contribution for player 1. You say, okay, well, given this order, I would add 1, and then, because remember, it's empty set union 1, and then you just look at the difference between the two, and of course that's 0, right? So this is also 0. 1 and 2 without 2 is 0, right? And then the only case that's actually got a payoff is when you union it with 3, in which case you get a payoff of 1. And so if you do this marginal contribution computation, right, so this is 1 over 6 for player 1. If you actually do this marginal computation for player 1, player 2, and player 3, you get the following: 1, 6, 1, 6, 2/3, right? So the person who has the, I think I ordered them wrong. This should be player 1, and these should be 2 and 3. Yeah. The person with the right-handed glove has the 2/3 payoff. Because 4 out of the 6 times they try it, they get a payoff of 1. Everyone else only gets a payoff of 1 out of the 6 times. Anyhow, the point being is that this is an example where the sum of it sums to 1, right? So efficiency is validated. If I were to add another player who didn't have any glove at all whatsoever, they would never have any payoff. And so, of course, dummy is satisfied. Symmetry is satisfied, for instance, between the two players who had the left-hand gloves. And then linearity is satisfied because you can imagine playing the same game again with the same players, and the sum of the Shap values would just be added up, and you would get to essentially double what you see here currently. So that's the glove game example. So I then promised an alternative way of formulating this. Rather than worrying about order, what if order doesn't matter? And so that is the farmer example done from the perspective of combinations. So assume we have a model. In this case, we have S as input. Note that it's not subscript with sigma, so order does not matter. It takes in S and it outputs F. Note that this is averaged over the results for every ordering of farmers. However, if the order doesn't matter, then it's moot, and so you can just output what the value would be irrespective of the ordering. And this does some of the hiding of the combinatorics, right? And so the key thing is, by phrasing it this way, if you don't care about order, the implementation of F can be more efficient. So you don't have to do the full double summation that you saw previously. So once again, this idea follows. For every permutation of farmers that are I, or this is literally the identical text, for every permutation is in I, you just take the difference, and that's essentially computing the marginal value. But you can implement it via F on every combination and let F handling the ordering only if need be. So this formulation here is mathematically equivalent to the prior formulation, assuming F properly implements the ordering if it matters. Right, so let me walk you through this. Once again, farmer I's credit. This is the exact same summation from before. It's the subsets from the power set of F minus I, right? F is the set of all farmers. The combinatorial normalization you see here, I'll explain in a moment. Don't worry about that. But the key thing is, once again, you have this subtraction between F with I and without I, right? So it's the same kind of subtraction, but it's doing it via F instead of V. So let's talk about this combinatorial normalization. Right, the key insight here is this is an unordered set, S, and S factorial is the number of ways to permute the preceding number of farmers, and this is the number, right, the inside of the parentheses is the number of succeeding farmers, and right, factorial is a number of ways to permute the succeeding one. You keep, of course, the farmer that you're reasoning about fixed, and you normalize this all by F factorial. That was the same as the 1 over F that you saw outside over here, right? This is just the same normalization. So assuming F properly implements all the combinatorics and everything, these are truly mathematically identical. You're basically just pushing notation around. So, right, remember that these handle the ordering of F, or of S appropriately. So with that in mind, I really want to harp on the idea that really the reason why anybody cares about these things at all is because of the 4 axioms that these things provide. Right? Efficiency, all of the Shapley values sum to the output. Dummy, if you have something that doesn't contribute anything, it gets no credit. Symmetry, if 2 things are the same, they get the same credit. And linearity, if they play 2 subgames, they do the intuitive thing of summing to the one whole game if you just model it as one complete game. So those are the benefits of Shapley. Now, there's also a bunch of problems. As I said before, computation is sharp P hard, which means it's very expensive in practice, right? The combinatorial explosion is a huge problem if you want to actually run this on a real system. And as was pointed out, you must be able to handle including and excluding farmers and get a meaningful real value out. And so a very reasonable question to ask is, what does this mean for non-artificial games? Right, so maybe I could just I don't know, will out of my head the notion of how each subset of farmers would operate. Alternatively, you might imagine running those actual experiments, or you might fit a model to some subset of the data using only those farmers and then claim that that's how you got there. But these are both big problems, but I'm actually going to focus on the latter one first because this one, I think, this one you just get more Google compute credits. This one is just a non-starter for a lot of problems. So we're going to focus on the second one first. So going from Shapley values to Shap values. So Shap values are Shapley additive explanations, and they were introduced by Lundberg et al. In 2017 in their paper, where they basically are trying to leverage the properties that Shapley values bring you while tackling their problems of computation. So one of the things that they do is, rather than having this bizarre definition of V, or F, which maybe solves a couple of the problems of V, how do you handle this where you have a bunch of data in a data table, and I want to compute Shapley values for the data table? And also, how do you then actually speed this thing up? It turns out you can use data structures to speed up the computation. And so by doing this, we're actually able to extend Shapley values to apply to general ML. Now, it's worth noting that nothing in life is free. There are things that you lose by doing this, and we'll talk about those in detail in a moment. So imagine that you have these data tables, right? So T is this table. You have N entries of P farmers or features. I'll just call them features from here on out. And you have yield or your Y values associated with the output. So you might well imagine this is a regression problem, right? You have some features input and an output here, right? You could imagine that these are farmers and like some information regarding how they actually participated. If you wanted to completely collapse this down in the old model, you might even imagine these are just bit strings telling you whether or not a farmer was participating. So you have this data table, and you want to compute Shapley-like values from it. So how do you fundamentally go about doing that? Right, because like the key thing is you need to figure out what to do about partial assignments for the P features. Because remember, as was pointed out earlier, you were reasoning about subsets. And yes, not only were the sets different sizes, you also had unassigned features you need to set some value to. Otherwise, it just doesn't mean anything. So we need to figure out how to assign these accordingly. So really fundamentally, right, this is the question. If I have this data table and I say that feature 1 equals 1, because that's what I'm piping into my F, how do I evaluate that? Right, that's really the million-dollar question. Is my high-level like equation from before said I fix F1 to be the value 1. What do I do? So there's a couple of ways you could do this. A naive way to do it is you just set all the other features to a nominal value, right? A cheap hack is set them all to 0, right? You could pick the mean or something for the feature. And that might work. I mean, this has some pretty big drawbacks. Namely, it might not even have an entry in the table. So you might have to do interpolation, right? You could linearly interpolate between 2 nearby points or something. And it's not guaranteed to actually uphold any of the Shapley properties, which is what we were going for to begin with. It might roughly approximate them, assuming that your nominal value is reasonable, but you don't actually get any mathematical guarantees from it. So what if instead we did marginal? So what you do is you basically take average over the table entries, fixing the fact that you wanted only to reason about data points where your feature is equal to this value. So in this example here, we fix feature 1 to be equal to 1, and then only reason about the entries in the table for which feature is 1, and we average the yield over both of them. Right, and that's what we would set F1 to. So this is actually what was originally proposed in the first Shap paper by Lundberg et al. The problem is this is impacted by sparsity. So as you saw, this only works because there are multiple entries in the table where F1 actually equals 1. It might be that in real world data, it's not quite 1. One of them 0.99, the other one's 1.001. You can do data smoothing, but when you do data smoothing, you start destroying the actual structure available in your data. The other thing that's worth noting is the conditional distribution, where you're actually conditioning on the fact that F1 needs to equal something, will impact the conditional, the distribution of your other features. And essentially what you're doing is you're trying to integrate over your other features. And by marginalizing on one of your first features, you're actually impacting this other distribution. So as a consequence of that fact, your computed marginal Shap values uphold efficiency and symmetry, but they do not uphold the dummy and the linearity axiom. And so this is actually proven in the I don't know how to pronounce this gentleman's last name, but in a paper 2 years later, the original Shap paper from 2017 said, we are computing Shapley values. Shapley values guarantee these properties. Therefore, all of our computations guarantee all of these properties. And it turns out that's not true. So that's something to keep in mind when you're reading the Lundberg et al. 2017 paper, is they misstated what properties their approach does and doesn't uphold. The other thing that's worth noting is the language that I'm using, right? Marginal, and I'm going to talk about conditional in a moment. Those are introduced relatively recently. So the literature on this is very new, and there's been some conflicts as a result of it's a bleeding edge field. So it's worth noting that this marginal essentially has some drawbacks, but it's not totally useless, and we can talk about that in a moment. And then there's also interventional. So before I was talking about how you could set F1 to be conditioned on, this proposes the do notation drawn from Perl. This was done in the early 2000s, where essentially what you do is you go in and you just set the value for every single feature in your data table to 1. And then you evaluate it accordingly. And this has a bunch of very strong assumptions that maybe don't follow well in practice. So this was proposed by Janzing et al. In 2019. The one thing that I actually forgot to mention is you would first, before you edit your data, you would fit a model to it. And then you would feed in the data values from the table into your model, having actually changed this feature here. So I mentioned the do notation, right? This, actually, let's just talk about the do notation first, just so everyone's on the same page. So imagine you have a Bayesian network, right? So you have some latent variable z. This is a thing you're actually trying to estimate, or rather, this is a thing that influences the 3 variables that you can observe. You can observe x1, x2, x3, and those all impact y. So the marginal approach conditions on the value of x1. But if you've worked with Bayes nets or studied classical AI or anything, you'll know that d-separation rules dictate that if you actually set this value to x1, because of how d-separation works, there's a chain of influence that influences z, which will then influence x1 or x2 and x3. So actually changing this value to be a set value will impact the distribution of x2 and x3, and so those won't be the same as the full distribution. The do notation that Perl suggests rather breaks the correlation between these two and simply sets this here and doesn't actually end up impacting the distribution of x2 and x3. Does that nuance make sense? Because you're setting essentially it over the entire data table, the distribution over F2 will just be the same as the full data table. If you're conditioning on it, it might be a different distribution. And so this is essentially this notion of the causality that it's forcing upon it. So, as I said, you would essentially fit a model to your data table and then take all the data in the data table, set the value for each feature that are being specified to the value you're told to set it to, and then pump it into your model. So this does a couple things. It assumes that the model that you fit to your data table is actually causal. That's obviously not necessarily, and almost certainly isn't true in practice, and it breaks feature correlations. So what I mean by that is imagine that you're training, or imagine the data table is medical data. So you're trying to predict, let's say someone's blood pressure. And as features, you have their age, their height, and their weight. So these are all clearly correlated with one another because babies do not weigh 250 pounds, and people who are 2 feet tall generally don't weigh 250 pounds. So if you were to condition using marginal, you would essentially only reason about the people that are exactly 250 pounds, if that's the thing that you're setting. But with the interventional approach, you're actually just saying every single entry in my data table, people weigh 250 pounds. So it doesn't matter if they're 6 months old and 18 inches long, they weigh 250 pounds. You're piping that into your model and assuming that your model is causal. And so that assumption is a very strong assumption. And it gives you some nice properties. For instance, efficiency, dummy, and linearity are upheld, but only under the assumption that your model is, in fact, causal. Now, note that symmetry is actually not upheld. And Doesnt et al. Actually devote a significant amount of time to discussing the symmetry axiom, what it means, and why it's actually okay that their symmetry axiom isn't upheld. So remember, the symmetry axiom is the axiom that says that if two people make the same contribution, they should get the same value for their contribution. Now, one of the things that's worth noting is that this notion of same contribution needs to hold over their entire input. So I will revisit this after we walk through an example of how you would actually use this on a data table. So applying SHAP, imagine that we have this data table. This is the same one as before. It's something I just invented. You would essentially want to compute a SHAP value for every single entry in this data table for every single feature. What I mean by that is, right, you have an n by p input data table with real valued outputs. You would compute SHAP values for every single entry here, right? So for row 1, right, so for entry 1, you would compute a SHAP value for feature 1, feature 2, all the way to feature p, and you would have a 0 mean y value associated over here. And the key thing, as I said before, is because of efficiency, these would actually all sum up to this y value over here. Right, so assuming efficiency is guaranteed, these all sum up to this y value, these all sum up to this y value over here, and these horizontally all sum up to this y value over here. The other thing is, because your y values are 0 mean, you can actually sum vertically along your table, and every single feature will sum up to 0. And essentially, the reason why that happens is for every entry, you're essentially, the value inside this table talks about your deviance, or the impact that feature had from your label's deviance from the mean. Right, so if your label deviated a lot from the mean, then there needs to be contributing factors in the features explaining why. And so that deviance needs to be split up among all of these features. If you sum vertically, the average deviance from the mean is 0. And so therefore, if you actually sum over all of the entries in your SHAP matrix, it'll just sum to 0. However, if you sum over a subset of the rows instead of all of them, it might not necessarily be 0. One of the things that you can do is actually sum the absolute value of the fees for each feature, right? So as I just said, if you sum these, they'll sum to 0. But if you sum the absolute value, you're essentially measuring the variance of each feature over all the inputs. And you can normalize by the number of inputs. And so that tells you essentially the mean amount that feature causes deviation from the output mean, right? How impactful is that feature from the output mean? So I said that I would talk about symmetry. One of the things that Doesnt et al. Argued is that their system, this interventional approach, doesn't uphold symmetry, but that's actually good, because while in aggregate, 2 features might make the same contribution, one feature might have a larger distribution than the other, right? The amount by which it impacts the outcome might be larger. And so in a scenario where, for any given scenario, and so in a scenario where feature A impacts the outcome more than feature B, even though in aggregate, the amount on average that they impact a feature in an absolute value sense is the same, it will give more credit to the feature that puts a large amount of deviance into the system, right? And their argument is that that justifies their quote unquote breaking the symmetry axiom in Shapley. Now, I'm like not totally sold on that argument, because that presumes that the distribution is Gaussian or some other normalized non-skewed distribution. If that is true, then their argument makes sense, but only under those conditions and only under proper data whitening do I think that makes sense. Because remember, these features could be literally anything. They don't have to be normally distributed or anything else.
Can I interrupt you for a second? Sorry. Can you go back to that table?
Yeah.
So, so going back to just the Shapley values, if these, the rows of these tables were 0, 1 vectors, right? Well, not this table really, but the table before I'm referring to.
Yeah. So the answer is yes. You might imagine them to be bit strings.
Right. If this was a bit string, then that would represent a certain subset, right?
Yes. And so I thought about intermediary presenting these just as bit strings and then generalizing to real values.
Right.
Yeah. So you might well imagine taking a Shapley problem and modeling it as a data table that way. And
right.
You could even go so far as to generate all of the F or P factorial different permutations. So actually, yeah, so that's the one thing that you're missing, is these don't currently reason about ordering.
Right, okay, so let's say if order doesn't matter.
If order doesn't matter, you might imagine the power set over all bit strings being represented here, associated with a Y.
Okay, and if you have that many rows, if you have 2 to the P rows, if n equals 2 to the P, then Shap should coincide with Shapley, correct?
Assuming the method that you use to compute the Shapley values upholds all of the same properties, yes.
Right, okay, because that's unique.
Correct. And as I said,
but the point we're making here is that you don't get symmetry for this method of computing.
Correct, you don't get symmetry for this.
Right, the interventional, you don't.
Marginal, you do get symmetry and efficiency, but you don't get dummy and you don't get linearity. And so you might not like the fact that you get symmetry, but something that is complete non-factor gets a non-zero value, essentially. Right, and that might be a thing that you don't want.
But the idea here is that if you think about this from a Bayesian point of view, then you don't have to make these n factorial computations. It's just linear, or it might be quadratic.
It's a function of your it scales with the number of entries in your table. I'm not sure if it's linearly or I think it would be quadratic. I'm not sure.
Something reasonable, log linear, quadratic.
The key thing in Lundberg et al. Is their argument was this was actually tractable to compute, kind of. Right. And so actually, naively, that still requires an exponential, right? Because you still need to do the power set. Yeah. Your computation of f is now more efficient, right? The inner function, but you are still doing this over the full power set of subsets of features. And so that's still a problem that we need to solve. And so that's something that I will get to. They have another
okay. So you're addressing, so this addresses the problem of the inner computation, but not the outer computation.
Right, and the inner computation was a problem because actually fundamentally modeling it was questionable under Shapley's original specification, right? You needed to know what to do about unassigned variables. This is a methodology to assign the variables using a data table such that you get at least some of the properties that you cared about from Shapley values originally, and depending on the methodology you use, you'll get different of those properties guaranteed versus not.
Got you. Thanks.
Right. So we talked about that. So let's now talk about, this is a perfect segue, how do you actually make SHAP tractable, right? Because this table enabled a more flexible definition of F, right? So it solved some of the problems where like you don't even know how to fundamentally structure the problem, and you have to forego some guarantees in order to allow for this more flexible definition. But we still need to fix the runtime, right? As I said, it still scales exponentially in the number of features because you're computing over the power set of the number of features. So we need to fix the runtime. So the proposal for this is called tree SHAP, and the idea is for marginal SHAP, the thing that you're essentially doing is you're trying to compute the conditional distribution over the features. Well, you're able to just condition on the branches already found in this tree. If you actually build this tree, right, this is a regression tree, right? So each leaf has a real value associated with it. The bins at the leaf nodes end up containing potentially lots and lots and lots of data points. And so rather than scaling with the number of entries and with the number of features, you end up actually being able to bin over the features. You actually end up scaling in the depth of the tree. And so now you've decoupled the computation. So instead of being the expense of the fundamental table, it's now how well are you willing to render the table inside this tree, and you're actually able to make this trade-off. So they actually did this for medical data to be able to allow real-time monitoring for anesthesiologists. So this actual implementation in the paper, the paper talks about doing this for marginal SHAP, right? That was the condition on, and it might change the distribution, and that's because you're like basically only looking at some of the buckets instead of all the buckets. But the actual implementation has an update from the Danzing et al. Paper, which came out around the same time, and they actually now support what's called a background data set. It's where you basically can set the full distribution over the branches in the tree. It's a lot more expensive to run. I'm not really sure of the runtime, to be perfectly honest with you. There's not literature on it. There's not a formal algorithm. I just read Python, and it runs a lot slower. So it might still be exponential. I'm not totally sure, but it's still faster than if you wanted to do it manually for the full combinatorics. And this is provided in the open source implementation of the Shapley package. So to do a review of where we started and where we ended up, we started with cooperative game theory. You had some function that was specified over partial inputs where order mattered. You then were able to abstract over the ordering and say, well, if order still matters, you can compute it inside this function. If order doesn't matter, then you can immediately compute it inside this function. But you still had to reason about partial definitions. We then talked about SHAP, which provides multiple different methods for actually doing the full assignment from the partial assignment, and different methods provide some of the guarantees that the original Shapley values provide. And now we've actually talked about tree SHAP, which builds a model over the top of these things and actually allows you to scale with the model as opposed to scaling with the number of features in the original data set. So does anybody have any questions? I believe, yeah, that's the end of my presentation. If people don't have it, I can talk about things I've used this for, applications, blah, blah, blah.
I guess one question that I had is it wasn't immediately clear why you would consider using SHAP in like a machine learning type problem. Or at least it's not immediately clear to me.
So I'll give you a concrete example. You want to explain a model, right? So all right, so there's two use. So the use case is explainable AI, and the reason why people use explainable AI is for two reasons, right? Psychologists take data, fit a model, and then try to explain the model, and by using the model explanation, they try to explain the world. There are machine learning practitioners who want to build a model that is very predictive, and then they want to explain the model so that they understand how the model works, right? So one of them is using the model as a proxy to explain the world and then explaining the model. The other one is explaining the model for the sake of explaining the model. So in the context of trees, because this is a very popular model, you want feature importance, right? How important is each feature in determining the outcome? And either that's because you want to know whether it's picking up on some structure that ought to be in the data because you're a domain expert and know the data, or because you're trying to learn about phenomena in the real world and you're fitting this model to try to explain it, right? One of the things that you can do is like entropy, what's it called? I have it written down. Give me like 1 second. Right, mean decrease in impurity, right? So you can compute the Gini coefficient for a node in each of its sub buckets. The problem is it doesn't really actually provide you any sort of guarantees at all. And worse, it actually really heavily favors high cardinality versus low cardinality features. And so a lot of the other explanations are very ad hoc. You, as a practitioner who are using them, need to understand that this is a very crude tool and that it has a lot of failure cases. And so you really need to eyeball it really closely to understand it. SHAP, of course, also has these, especially if you're using Marginal or something else where a feature could even be non-zero for no reason. But it's important to keep in mind that SHAP provides a lot more in terms of mathematical guarantees than basically anything else out there. And so that's really, I think, the compelling reason. So for instance, like one of the things that people do in social science is they'll have a bunch of data, they'll fit OLS to it, and then they'll use the weights on each feature to justify how important that is. And that's like standard practice in social science. Even if the features themselves aren't Gaussian, even if there's non-linear interactions between the features, like this is just still how they do that. This offers an alternative that actually provides more guarantees to you with regards to how to actually go about solving the problem.
Okay. So I might be thinking about this wrong, coming more from deep learning, that you train certain, you train the parameters for a model, let's say, and you want to understand like how much like equity each training parameter has, or maybe I'm thinking about this wrong.
Okay, so you're thinking about this from the perspective of structure internal to your quote unquote black box model.
Right.
This is abstracting over so tree SHAP obviously reasons about the structure to some degree, but you can imagine not using tree SHAP, but instead literally just treating whatever model. It could be a neural net, it could be a linear model, it could be quadratic, doesn't matter. Right? You could imagine treating that as whatever your F function is. And as long as you use something that fully specifies all the parameters, it doesn't care about the structure. It says, for this specific data point, where these were the feature inputs, what parts of them, right? Like which features are the ones that encouraged you to give this prediction as an output, right? You predicted blah, blah, blah. What?
Oh, so that's a little counterintuitive because it's interpretability without actually looking inside the black box at all.
So, it's using the structure of the outputs of the black box, given the structure of the inputs of the black box, to determine the importance. It's not actually fundamentally looking at the structure, right? It's not turning the black box into a gray box or white box model, right? It's not actually inspecting the underlying structure present inside the model and saying, yes, this is the region of your neural net that made that decision.
Okay. All right. So now, and maybe you mentioned this in the talk, but okay, so you have a bunch of features and a bunch of outputs to your model. And from that, you can calculate the Shapley values in a number of ways, but you mentioned a few. So then how does this sort of inform interpretability from here?
So I'll give you this example. The idea is that even if you don't know anything about the domain, you just know that the feature worst radius had a much higher degree of impact on the output. Right? You don't even need to know what it's predicting. Then
Right.
followed by concave points, followed by worst connectivity, followed by worst texture. One of the guarantees that they actually make in the tree shap paper is that while the magnitudes of these things may change, the relative ordering will stay constant no matter what the model structure of the tree is. And so this was important because they are arguing that every other feature importance measure, if you were to train the tree with a different random seed, could potentially swap importances. Where you could end up with a thing that was fundamentally higher, so the rank ordering is different and quote unquote wrong. Whereas they give a consistent rank ordering.
Okay. So this rank ordering is ultimately useful for science, understanding why certain features are more important than others.
So a concrete use case for this is, imagine you're a social scientist, you have a data set that you're trying to predict some societal outcome given a bunch of features about people. You want to know what features about people are correlated with the societal outcome that you're interested in studying. So one of the things you can do is take your really, really, really big data set with a lot of features, fit a tree. And by the way, you can overfit your tree because you're actually trying to train and test on the same data set. So it's totally okay to grossly overfit your tree.
Yeah.
You can then use one of these SHAP approaches to then explain the model of the tree. And by doing that, you're explaining the structure present in the underlying data. And so you actually get things out like, oh, this feature on people is correlated with this societal outcome that I'm interested in studying. And so I think in that regard, this is actually a really brilliant tool that will allow social scientists to stop just spitting an OLS and then being like, this weight highest, clearly this feature most important. That's the thing that's correlated with these outputs. Because I've read some social science papers where they fit that on a thing that was very clearly not Gaussian, right? Because OLS makes a very strong Gaussian assumption about
Right.
features.
Cool.
So this is an example where you can take very nice, although a little bit abstract, multiplayer cooperative game theory and apply it to something that is very, very actionable, very concrete, very useful. So I took an Explainable AI seminar last semester. This was one of my favorite results is SHAP and related stuff. So I actually wrote a quasi-summary paper about these methods, have a little bit more math, and in examples based around classification on my webpage, right? And that was my final project for the class.
Nice. So I saw that paper, and now I think I could read the paper.
Yeah, the paper does not do an appropriate introduction for beginners.
Cool. Yeah. So now I could read it, and everybody else here can too. So do we have any